Hello everybody, welcome to you all to this MOOCs online video course Theory of Yarn Structure. In the last class we started module 9 strength and length relation in yarn. We were discussing about FT Peirce model. We introduced Peirce 3 assumptions. One was related to strength independency, second was related to principle of weakest link, and third was related to Gaussian distribution at smaller length of yarn. Then we were trying to establish the relationships between probability density function of strength at shorter length and probability density function of strength at longer length, and also distribution function of strength of shorter length and distribution function of strength of longer length. So, that we did. Then we were discussing about the transformation. So, sometimes strength S at longer length L is transformed. This is not standardization. The word standardization we have used for shorter length, but here we are using transformation. How we do transformation? This transformation is generally done in this way. Say U is equal to, this is the strength at longer length minus this is the mean strength at shorter length divided by standard deviation of strength at shorter length. Try to understand. This is the strength at longer length L minus mean strength at shorter length divided by standard deviation of shorter length. So, this quantity we name it as U. So, how we find out strength at longer length? S is equal to mean strength at shorter length plus U sigma naught. So, what will be happening if we differentiate U with respect to U? Sigma naught du. The U will vary from minus infinity to plus infinity. So, this transformation makes our calculations relatively easy. Now, as capital S strength at longer gauge length is a random variable, U also a random variable. Any random variable is characterized by its probability characteristics and statistical characteristics. The probability characteristics include probability density function and distribution function. The statistical characteristics include mean, standard deviation, variance, skewness, kurtosis. Basically, they are the moments. So, we will now establish the probability characteristics and statistical characteristics of U. First, we will start with the probability characteristics of U. First, we will discuss about the distribution function, capital G U L. Now, what we do? We substitute. Let us find it out. say U to this FSL. What was the form of FSL? 1 minus S minus by sigma naught to the power L by L0. So, if we substitute this, what we obtained? Then we obtain G U L. G U L is equal to 1 minus uppercase phi U L by L naught. Right. This is how we obtain distribution function, and the second probability characteristics is probability density function. We use the symbol small GUL. From the theory of probability, it is valid that GUL du is equal to FSL ds. Why it is valid? Because this is the probability of U, and this is the probability of S. S is transformed to U, their probabilities must be same. That is why this relationship is valid. Now, using this relation, we can easily obtain what will be this FSL into ds by du. ds by du is sigma naught, and what is FSL? We know very well. So, G U L du is equal to ds. This is equal to 1 L by L naught into 1 by sigma naught into phi S minus S naught by sigma naught, right, into 1 minus uppercase phi S minus S naught sigma naught to the power L minus L naught by L naught into ds. ds is sigma naught into du, that is equal to ds, isn't it? So, this du and this du cancel out. What we obtain is an expression for PDF of G U. L by L naught sigma naught phi into 1 minus phi L naught. Right. We can further write it as L by L naught into this 1 by sigma naught into phi is related to the PDF of u. So, this is your phi of u, right, into 1 minus phi of u, L minus L naught by L naught, right. What is phi of u? L by L naught, 1 by root over 2 pi to the power minus u square by 2, right, into what is this expression? 1 minus 1 by root 2 pi in 1 by root 2 pi, okay, into integration minus infinity to u v square by 2 dv to the power L minus L 0 by L 0. So, let us write down it in a better form. G u L is equal to L by L naught into 1 by root over 2 pi e to the power minus u square by 2 into 1 minus 1 by root over 2 pi into integration minus infinity to u v square by 2 dv to the power L minus L 0 by L 0. L by L 0 root over 1 by root over 2 pi x to the power e to the power minus u square by 2. This is your phi of u, lowercase phi, into 1 minus 1 by root 1 minus 1 by root 2 pi no, the bracket will be here, not here, the bracket will be here, not here, 1 minus 1 by root 2 pi into integration minus infinity to u minus v square by 2 dv to the power L minus L 0 by L 0, right. All right. Now, this expression, it is possible to solve this expression using suitable numerical method, and I will show you the graphical behavior of this equation. This is the graphical behavior of this equation. U is plotted along x axis, PDF of u is plotted along y axis. What we see is that when, look at the thick line, thick curve, L by L 0 is 1, it is Gaussian. In all other cases, if it is smaller than 1 or if it is higher than 1, in all other cases it is not Gaussian. That means, you remember we have already assumed at short length it is Gaussian. So, this is the distribution at short length. In all other lengths it is not Gaussian. All right. So, now we proceed to obtain the statistical characteristics of u. As I told you, u, a random variable, is characterized by its probability characteristics, and also by its statistical characteristics. So, that statistical characteristics we will now discuss. Statistical characteristics are often talked about two aspects, non-central moments and central moments. What is non-central moments? Non-central moments is the moments about origin. So, for example, mth non-central moment of u is u to the power m bar u to the power m into g u l du, when this will be minus infinity to plus infinity, right. Now, you know the expression for g u l, here it is. So, if this expression, this long expression you substitute here, if that integration is solved, you will come to know about the mth non-central moment. Similarly, you can express mth non-central moment of S. From U also you can obtain S. What is that? This is equal to minus infinity to plus infinity s to the power m into f SL ds. Now, you know what is f SL ds, earlier we have already derived. So, you can find out this. Let me write for u minus infinity to plus infinity. What is s? S is plus this transformation to the power m, and what is FSL? FSL is G U L ds. FSL ds is equal to G U L du, relative frequency probability remains same, right. So, this can be further written as I is equal to 0 to I is equal to m, m c I sigma naught to the power m minus 1 u to the power m minus 1 s to the power I, right, into G U L du. So, again by solving this you will obtain the mth non-central moment of S. Then comes about central moments, moments about mean 2. Central moments of U. So, moments about mean. Say for example, u minus u bar, u bar is the mean of u, to the power m, right, and mean of that. So, what is that? Expectation, expectation of u minus u bar to the power m, right. So, this expectation can also be find out. Similarly, we can find out. So, this is your mth central moment. Of u. Similarly, we can find out mth central moment of S. Mth central moment of S. How we can find out? S minus this to the power m this. So, it is basically E S minus the power m, right. So, what is your S? S is your sigma naught into u plus this is your S, and what is S bar? What is your S bar? S bar will be sigma naught u bar plus S naught to the power m. Okay. So, what you will obtain? You will obtain sigma naught to the power m u minus u bar to the power m, right. So, this is a constant, will come out of this e to the power u minus u bar to the power m. So, that is basically u minus u bar to the power m of mean of this, right. So, for different values of u, you will be able to find out central moment of S and u. If we now put m is equal to 1, 2, 3 in these equations, we will obtain different moments. For example, mean value, u bar minus infinity to plus infinity u g u l du, right. And if I convert into S bar, sigma this into u bar plus this, right. Mean of u, mean of S, both can be find out. Say variance, what is variance? Variance is sigma u square, variance of u, variance of S, both can be found out. Sigma u square, u minus u bar square, this, right. Using this we can find out the variance. So, variance of S sigma S square S minus this square. So, that will be basically sigma square into sigma u square. Then standard deviation is the positive square root of variance. Sigma u is the this, sigma s is the another useful term often we use coefficient of variation. Coefficient of variation nu of u, standard deviation by mean. Similarly, coefficient of variation for S bar sigma S by S bar. These are dimensionless form. However, if you multiply by 100 you will get it in percentage. Another two characteristics are often used, one is called skewness, second is called kurtosis. Let me tell you what is skewness. Skewness characterizes the lack of symmetry of a distribution, measure of lack of symmetry of the distribution of a data set. This we use a symbol A. How we define? Skewness is defined by this to the power three by 2. So, this is how we obtain skewness. If I use S minus divided by square, S by square and to the power 3 by 2, is not it? To the power 3 by 2. So, this is about your skewness. Another terminology is kurtosis. Measure of pickedness. How much is the peak actually of a distributed data set? Relative to Gaussian distribution. So, also you can find out kurtosis for u, kurtosis for S. Kurtosis for u bar to the power 4 divided by u minus u square to the power square minus 3 is the expression for kurtosis for u, and also similarly we can find out kurtosis for s minus s bar, this s minus s bar squared to the power squared minus 3. So, we talked about mean, variance, standard deviation, coefficient of variation, skewness, kurtosis, all can be found out. Now, all these behaviors, all these equations were used to find out these statistical characteristics for different ratios of lengths. So, all these equations we have written so far were used to find out this one. For example, u bar, integration minus infinity to plus infinity u into g u l d u. So, that equation was solved to find out u bar. Right, here it is, u bar. This equation was solved for different values of L by L naught. Similarly, variance, standard deviation, skewness, kurtosis, all you can see here. When L by L 0.1, this is the value of u bar, this is the value of standard deviation of u, this is the value of coefficient of variation of u, this is skewness, this is kurtosis. So, this is L by L naught, this is u bar, sigma of u, nu of u, a, e for different values. Interesting to observe is that when it is one shorter length, mean is 0, standard deviation 1, this is plus minus infinity, a 0, e 0, because it is normal distribution, right, because it is normal distribution. So, in all other cases you see, for starting from 0.1 to say as high as 1000, we can find out all this. Now, these, now what we can do, we can plot this along x axis and we can plot all quantities along y axis. Peirce did that to obtain original behavior. For two quantities are of important now, one is u bar, another is sigma u, mean value of u and standard deviation of u. So, that I will show you here. For different values of L by L naught, this is the thick line is basically the u bar. So, thick lines are the original one. So, this is for u bar and this thick line is for sigma u. You can see that there are also thin lines, say for u bar this is a thin line and for sigma u this is a thin line. What is a thin line? Thin lines are some approximated original we understand, original is coming from these equations what we wrote earlier. What is the approximation? Peirce approximated these relations. How? You know. Peirce approximated this u by this. So, this is approximated by L by L naught to the power minus 1 by 5. So, these are the approximations used by Peirce, and for u bar Peirce approximated by this 4.2 into L by L naught minus 1 by 5 minus 1. This is how Peirce approximated all these original values. You can see that these approximations are quite well so we rewrite Peirce strength length relations. Sigma S is equal to sigma naught L by L naught to the power minus 1 by 5 and S mean is naught plus 4.2 sigma naught L minus L naught to the power minus 1.5 by this. These two are the well known expressions which are often used to predict the strength at longer gauge lengths, and this is the way these two expressions are derived. The bottom one, this is the mean strength at longer gauge length L, this is the mean strength at shorter gauge length L naught. 4.2 is a multiplying factor here into standard deviation of strength at smaller gauge length. L is the longer gauge length, L naught is the smaller gauge length. So, this characterizes the mean strength at longer gauge length, and the upper one, top one, characterizes the variability of strength at longer gauge length. This is the standard deviation of strength at longer gauge length, this is the standard deviation of strength at shorter gauge length, this is the longer gauge length, this is the shorter gauge length. So, these by using these two expressions we can predict the mean strength as well as variability of strength of yarn at longer gauge lengths. Now, sometimes these equations are written in a different manner. In some books, some research papers, you will find out that. Let us consider A is equal to S naught minus 4.2 sigma naught, basically this one, 4.2 sigma naught minus 1 and B is equal to sigma naught L naught to the power 1 by 5. Then we can write A star A plus B L to the power minus 1 by 5. Why do we write in this form? Because here S is the strength at longer gauge length, L is the longer gauge length. These two parameters A and B are related to shorter gauge length. So, that is why also sometimes it is expressed in this form. Right. So, this is how Peirce obtained the two famous relations which are often used in textiles to predict the strength at longer gauge length. Now, we would like to see how these two equations correspond to reality. So, we have produced a yarn 7.4 tex cotton combed ring yarn. So, this gives you a comparison between Peirce equations and experimental results. Let us write down first Peirce equation. We have derived two equations. One is the mean strength at longer gauge length is equal to mean strength at shorter gauge length plus 4.2 into standard deviation of strength at shorter gauge length into longer gauge length divided by shorter gauge length to the power minus 1 by 5 minus 1. So, this is your first equation related to mean strength, and the second equation is related to standard deviation of yarn strength at longer gauge length is equal to standard deviation of yarn strength at shorter gauge length into longer gauge length divided by shorter gauge length to the power minus 1 by 5. So, these two are the Peirce's equation, and now we will talk about the experimental results. So, we have taken a cotton combed ring spun yarn count of the yarn was 7.4 tex. For experimental verification purpose, this yarn was tested at different gauge lengths. And this graph compares the Peirce's equation with experimental results. First, we talk about this equation. The behavior of this equation is shown by this line This is from Peirce theory, the behavior of this equation, and the small circles denote the average strength at different gauge lengths, experimental results. And this equation is plotted here at the bottom. The small circles here denote the standard deviation of yarn strength at different gauge lengths. What we see is that there is a close association between theoretical results and experimental findings. So, Peirce's theory corresponds quite well with the experimental results. However, there is one more theory available on strength length relation in yarn based on yarn strength as a stochastic process. However, that theory is not included in the syllabus of this course. So, Peirce theory corresponds quite well with the experimental results. Now, we will solve a few numerical problems related to Peirce theory. This is the first numerical problem. This problem reads as follows: a 500 millimeter length of yarn is divided into 10 sections of equal length. So, we have the following information: 500 mm, n is 10. So, of course, L naught is millimeter. Each of the 10 sections exhibit same probability of breakage. So, if S L naught is equal to 0.2, what is the probability of breakage of the entire yarn? What is the probability of survival of the entire yarn? We know that probability of survival of length L is equal to probability of survival of length L naught to the power n number of sections. So, if SL, if this is the probability of breakage of a longer length L at a force S, then 1 minus FSL is the probability of survival of the yarn of length L at a force S, which is equal to probability of survival of smaller length L naught to the power n. So, what is given? 1 minus 0.2 to the power 10. So, 0.8 to the power 10, this value is equal to 0.1074. So, this is the probability of survival. So, answer of the second part of the problem. What is the probability of survival of the entire yarn? The probability of survival of the entire yarn is 0.1074. And then what is the probability of breakage? Probability of breakage of length L is equal to this, which is equal to 1 minus 0.1074. So, which is equal to 0.8926. So, this is the answer to the first part of the problem. What is the probability of breakage of the entire yarn? The probability of breakage of the entire yarn is 0.8926. So, this is the solution of the first problem. Now, we come to the second problem. The second problem reads as follows: the strength of 50 millimeter length of a yarn follows Gaussian distribution with mean at 10 cm per tex and variance at 4 cm per tex square. What is the probability that the strength will exceed 12 cm per tex? It is basically a problem of Gaussian distribution. This problem is quite interesting. The solution is very easy. Let us solve for this problem. Now, what is given? Given is this 10 cm per tex and sigma naught is given 4 per tex, that is equal to 2 cm per tex, because we know that standard deviation is positive square root of variance. If variance is 4 cm per tex square, then standard deviation is 2 cm per tex. What you are asked for? You are asked for probability that the strength will exceed 12 cm per tex. So, you are asked basically probability of strength which is greater than 12. You are asked to find out this probability. Okay. Now, strength at 50 mm gauge length follows Gaussian distribution. So, we will now find out this probability. Let U or V is equal to S minus S naught by sigma naught. S is the strength, all are related to same gauge length. Now, S follows normal distribution. So, this is standard normal variable V. So, V of course follows normal distribution. S minus, this is not transformation, this is standardization, because S is related to the same gauge length, minus 10 by 2. So, we obtain S is equal to 2 times V plus 10. V is standard normal variable. So, P 2 times V plus 10 greater than 12, P V greater than 1. So, in a normal distribution, if this is V, this is suppose PDF of V, then this is 0 and this probably is 1. So, you need to find out this probability. How will you find out this probability? The entire probability is 1. So, 1 minus the this probability, 1 minus this gives the answer. So, we can write down this as 1 minus probability of V less than equal to 1, right. So, this is the uppercase phi 1. So, how to find out this? There are two ways of doing this. One, starting from basics. Second, these values are generally available in so called normal standard normal table, which is available generally at the end of any statistics books. So, we can consult those tables and we can directly write these values. However, suppose the table is not with us. Under such circumstances, how to solve this? There is a way of doing that. However, it takes some more time. Let us do that. We have to find out this distribution function, right. So, minus infinity to 1 G V dV, right. This we have learned in the theory part. So, V is standard normal variable, minus infinity to 1, what is V? G V, 1 root over 2 pi e to the power minus V square by 2 dV. So, if you come to this table, that means we are trying to find out, suppose let us use this color, green color. We are trying to find out the area hashed with this green color, right. Now, normal distribution is a symmetric distribution. So, from minus infinity to plus infinity, minus infinity to 0, the total area is 1, symmetric distribution. So, minus infinity to 0 is always half. So, minus infinity to 0, 0.5 plus 0 to 1. So, we can find out this limit. So, this we can write down in this manner: minus infinity to 0, this probability plus 0 to 1 this probability. Why we do this? Because we know this is half of the total area available under the curve, which is equal to 0.5. So, we write 0.5 here plus 0 to 1 by root 2 pi minus v square by 2 dv. How to find out this? This one can be found out in the following manner: 0.5 plus 1 by root 2 pi 0 to 1 e to the power minus v square by 2 dv. We know the series expansion of e to the power x, the same formula we will apply here: 0.5 plus 1 by root 2 pi integration 0 to 1. So, 1 minus v square by 2 plus v to the power 4 by 8 minus v to the power 6 by 48 plus v to the power 8 by 384 minus v to the power 10 by 3840 plus v to the power 12 by 46080 minus likewise into dv. Now, this integration is very easy. We will do it in the next page. So, we were trying to find out the value of this, which we came to know 0.5 plus 1 by root 2 pi. Now, we will do this integration. Integration of 1 into dv v. So, in this way we find out all integrals and we write down v minus integration of v square by 2 into dv v cube by 6. So, we write v cube by 6. Next, integration v to the power 4 by 8 into dv v to the power 5 by 40 v to the power 5 by 40. In this way we continue. Zero to 1. So, we can easily find out this value. This value will be 0.5 plus 0.34 1190 up to 6 decimal places. So, which is approximately equal to 0.8412, right. So, now we come back to our problem. We need to find out p is greater than 12, probability of s greater than 12, 1 minus uppercase phi 1. So, we come back to find out the answer s greater than 12, 1 minus phi of 1. So, 1 minus 0.8412, 0.1588. This is the answer to the problem number 2. So, if the table would have been there, directly by consulting this table we could find out this value, but if the table is not available, then we can find out in this manner. It is a little time consuming, however, there is a learning associated with it. Nevertheless, the answer to this question is 0.1588. Now, we come to the third problem or the last problem of this module. A yarn was tested for its strength at a gauge length of 50 millimeter. Numerical problem 3 reads as follows: a yarn was tested for its strength at a gauge length of 50 millimeter. The mean strength and the standard deviation of strength were obtained as 20 cm per text and 2 cm per text respectively. Predict the mean strength and CV of strength at 500 millimeter gauge length. This is direct application of Pierce problem. So, what are given? Given this 20 centinewton per text and this is given as 2 centinewton per text. We apply Pierce formula. Mean strength at longer gauge length 500 millimeter gauge length is equal to this plus 4.2 sigma naught L by L naught to the power minus 1 by 5 minus 1. So, we apply the values 20 plus 4.2 into 2 into 500 by 50 to the power minus 1 by 5 minus 1, this and this. So, this value you will see 20 plus 8.4 into minus 0.3690. This value will be equal to 16.9 centinewton per text. This is the mean strength. Now, we have to find out CV of strength. So, let us now find out standard deviation of strength. S sigma is equal to sigma naught L by L naught to the power minus 1 by 5. So, sigma naught is given 2, 500 by 50 to the power minus 1 by 5. This value will be equal to 1.262 centinewton per text. We are not asked standard deviation, we have to find out the value for CV. So, CV we know standard deviation by mean dimensionless. So, 1.262 divided by 16.9, what will be the value? 0.0746. If you would like to express CV in terms of percentage, then it is 7.46%. This is the answer of CV. So, this is the solution of the problem number 3. So, all numerical problems of this module are over, solved now, and module number 9 is completed. Thank you for your attention.